So that's working.
The two-tail thing, I asked Ben and he said it was lifeline. Yeah, he said lifeline. Did you pick lifeline? Okay. I mean, if everybody's confused on that one question of hidden nitrogen, I'm assuming he'll probably drop it. Yeah, that's what I had, and that was all base. That's what I had, because I didn't have one that was yellow.
We've all been discussing questions.
Yeah.
Different questions on our exam.
No, we all have the same exact question.
So
Just
we're
different
just catching
order.
up on what we remember.
That actually happens for some reason. I don't know why, but it is. I can tell you for sure it's the exact same question, just different orders. So. All right. So. All right. And in fact, I think I'll draw a little bit here. We'll do it that way. All right. So we're going to get started. We're going to try to finish chapter 13A stuff today. Before we get to the worksheet questions, we're going to review a little bit of the stuff we went over last SI session. The most important thing in terms of understanding enzyme kinetics is being able to visualize how an enzyme interacts with its substrate. And we'll start, of course, with the Michaelis-Menten theory. Is the lighting all right here? You guys able to see? Or should I? Okay. So, Michaelis-Menten theory. And the Michaelis-Menten theory is basically this. You have an enzyme, and you have a substrate. The substrate is going to bind to a particular site on the enzyme called what? Anyone know what the site is called on the
Active
enzyme?
site.
Active site is exactly right. So that is the active site. And enzymes, Michaelis-Menten enzymes, allosteric enzymes, they have extra sites also, which I didn't really draw in here, but I'll draw one right here. That is not where the substrate binds to. What do they call these sites? These are allosteric sites, exactly. So active sites are where the substrate goes to. Allosteric sites are where other molecules can go to, which we'll talk about today. I believe we'll get to it in time. So the Michaelis-Menten theory is that there's a substrate, there's an enzyme, and there's an active site. The substrate binds to the enzyme at the active site, and you create what is called an enzyme-substrate complex, which is kind of like an intermediate between, in the reaction of converting the substrate into product. So this is the enzyme-substrate complex, which is one of the core components of the Michaelis-Menten theory. Then, if enough energy is applied, the enzyme will be able to convert the substrate into a product, and the enzyme returns back to its normal self, And the enzyme can go and find another substrate and catalyze it. There's stains on this camera, it looks like. Or no, is it the screen? No idea. Yeah, so after the enzyme converts the substrate into product, the enzyme is free to pick up another substrate and continue. So this is the visualization of an enzymatic reaction, and in particular Michaelis Menten. Allosteric enzymes, it's a little bit more complicated. There's more arrows and stuff. We'll talk about that when we get to it. So this reaction can be characterized by a few mathematical variables. One is Vmax, and another is Km. These are the two most important ones, and there's some other ones you can calculate on the side. We will get to those later. So to describe it, Vmax is the maximum rate of this reaction. Is what is the fastest possible speed at which the enzyme is able to catalyze this reaction. So that one's easy. Max speed of reaction. And the reason why there's a max speed is that enzymes are not infinitely fast. Eventually, if enough substrate is added, the enzyme will reach saturation. It won't be able to break down substrate any faster. If we go with Dr. Hasey's analogy, and I'll break that down again, his analogy is his brother or relative or something is the enzyme. And the substrate, and he changes the fruit sometimes, but the substrate is the apple, okay? So with his analogy, basically, his brother, the enzyme, grabs onto apples, the substrate. We see that's the first thing that happens here, is the enzyme grabs onto its substrate. Then the brother brings the apple to his mouth, bites it, and converts it into product. That is the enzyme converting the substrate into product, okay? With his analogy, though, his brother is only able to grab like 10 apples at a time, per second is what I should say. He can't go any faster than that. So if he throws 20 apples at his brother's still only going to be able to bite 10 of them at a time. He has reached the saturation point for his brother, for his enzyme. So the saturation point, meaning the maximum amount of substrate the enzyme can convert, meaning the maximum speed, is what Vmax is. On a graph, that should be one of the easiest things to be able to identify. This enzymatic reaction will have this shape on a graph, where that's speed and this is substrate concentration on the x-axis. Vmax is simply this asymptote up here, which you can easily read on the graph. Yes?
That part leading up to the asymptote, is that linear or is that curved?
This part is curved. The whole thing is curved, and this last part is linear. It's just didn't draw it too right. But yeah, this it follows a hyperbolic shape, is what they call it in algebra or calculus or something. But yeah, it follows this trend. In chemistry, you guys learned about like orders of reactions, like zero order, first order, second order. You don't need to know about it in as much detail here as you did in Gen Chem. Although the notes and some of my old worksheets went over it, the only thing you really need to know is that at low substrate concentration, the reaction order, actually, does anyone know, what is the reaction order approximately? Zero, first, or second? It is first order at low substrate concentration, which is a fancy way of saying the speed of the reaction is approximately increasing linearly with substrate concentration. Approximately. Obviously, it isn't a straight line, but it is approximately linearly increasing with substrate concentration when there is low substrate concentration. When there is high substrate concentration, we see the line flattens out. What is the order of the reaction now?
Second. Zero.
Is zeroth order. Zeroth order is the one when it doesn't change at all, no matter how much substrate concentration you get. Yeah, so it turns out Michaelis Menten enzymes are unable to do second order reactions. When we get to allosteric, you'll see that they're able to do second order. So what was I saying? So yeah, this is zeroth order at high substrate concentration because it's reached saturation. It can't get any faster than it's going right now. Okay, so that's what they mean when you look in the notes and they say low substrate concentration, first order, high substrate concentration, zeroth order. It is simply they're trying to describe the shape of this graph in approximations.
Can you repeat one more time what you meant by zeroth order?
Yeah, zeroth order is basically a chemistry way of saying if you add even if you add more substrate, it won't go any faster. The rate is constant, is the general chemistry term. The rate is constant. And notice that is only true for high substrate concentrations, because the left half of this graph, which is quote-unquote low substrate concentrations, very clearly the rate of the reaction changes with the amount of substrate. Okay, so that covers Vmax. Again, very easy to identify on a graph. Just look at where the graph reaches its saturation point. Whatever the velocity is at this spot here would be your Vmax. Okay. Any questions on this? Because I'm going to have to start a new page. Okay. Again, make sure everything's still recording. It is. Okay. Next value is Km. So this one, as I talked about last SI session, Km, think about it conceptually as just the enzyme's ability to grab onto substrate. With, so actually let me write that down first. Enzyme ability to grab substrate. Obviously there's more scientific terms for it, but I don't care. That is how I see it. With Dr. Hasey's analogy, Km is a number that describes how well the brother does at catching apples thrown at him. Km does not describe anything with how fast the reaction goes, with what product is made. Km is a number that describes the enzyme's ability to grab onto substrate, his brother's ability to grab onto apples, basically. Yes?
One of the worksheets that he posted, it said that Km was also like the dissociation constant or something.
Yeah, if we want to go into, and that was an old question. It may show up on this exam, I don't know yet, but yeah, let me go over some vocabulary terms. Km sometimes is referred to as a pseudo-dissociation constant. And I'll explain what that means. Okay. Now remember, it is my opinion that I think it is best for you to think of Km as a number that describes the enzyme's ability to grab substrate. However, you go into really technical textbook definitions, Km is a combination of three numbers. And let me draw something real quick because I never remember it off the top of my head. K1, K minus 1, K2. What is it? I think it is K minus 1, K2 over K1. Some combination like this is the actual value of Km. The reason why we call it a pseudo-dissociation constant is that this number here depends on the numbers I've just circled there, which is numbers that describe the rate at which the enzyme lets go of its substrate. So it's called a pseudo-dissociation constant because technically Km is a value that describes how quickly an enzyme lets go of its substrate. I wouldn't bother concerning myself with exactly what that means. I would just memorize, if it shows up, Km means a pseudo-dissociation constant, but conceptually what will help you answer mathematical questions, I would remember this one. It describes the enzyme's ability to grab substrate. Yes?
Do we have that formula?
No. So the only formulas you're going to need to know, I'll point out today, but most of the formulas that are, if you read the PowerPoints, they say you need to know how to derive the formulas. No, you don't need to know how to derive any of the formulas. That's an old feature of the PowerPoints, and I think is probably still up there to kind of, poke fun at the students that don't show up at class, that just read the PowerPoints and stuff like that. But no, you don't need to know how to derive any of those equations. There's really only 2.5 equations that you need to know, and I'll give them to you when we're working on the worksheet. So yeah, pseudo-dissociation constant is just a term to associate with Km. Oh, and very important, a smaller Km means enzyme grabs, again my grammar is bad, grabs tightly to its substrate. Basically, if you have you want as small of a value of Km as possible. It means the enzyme is really good at grabbing onto substrate, which is the first step in the enzymatic reaction process, is you aren't going to be able to catalyze any reaction if the enzyme is bad at grabbing onto substrate in the first place. So a smaller Km is good. Okay. Okay, so we talked about Vmax, we talked about Km. All right, those are the two main important variables to talk about when we're talking about enzyme kinetics. There's a few bonus ones, though. One of which is something called Kcat. Okay. Kcat is a number that describes basically the maximum rate that one copy of an enzyme can catalyze a reaction. Vmax, for contrasting purposes, but you don't need to know the reason why, I'm just going to tell you anyway, is that Vmax describes the maximum rate of an overall reaction, meaning if you got 10 enzymes, Vmax is calculated based off 10 enzymes. Kcat, however, is the maximum rate of one of those enzymes. That's it. So your notes, your PowerPoints will have a different definition, that's fine, but the basic mental idea of what Kcat is, it's basically Vmax of one enzyme. Because of that, Kcat will always be a constant value for a particular enzyme. You can look up the Kcat of catalase. You can look up the Kcat of any glycolysis enzyme. It will be a constant value written in a table because it was measured for one copy of that enzyme. Vmax, on the other hand, will change depending on the reaction conditions that you're dealing with. Okay. The other value, oh yeah, let me give you the formula for Kcat, my bad. Kcat is simply calculated, and you may be asked to calculate Kcat, is simply Vmax divided by the enzyme concentration, not substrate concentration, divided by the enzyme concentration, which would have to be given to you in the problem. Okay. So Kcat is Vmax, which you may calculate in other methods, divided by the enzyme concentration. The other formula we need in terms of this extra stuff is catalytic efficiency. Okay. Catalytic efficiency is simply calculated as Kcat over Kn. That's all it is. Catalytic efficiency is Kcat over Kn. Now, what is catalytic efficiency? Catalytic efficiency is probably the most important property of an enzyme because it just tells you how efficient it is. What that means is a lot of enzymes may not be efficient, but if there's plenty of substrate around, who cares? It's still going to be able to do its job. An enzyme that is efficient will will be able to catalyze reactions very quickly whether there's a lot of substrate or not a lot of substrate. You go look at your PowerPoint definition, you know what, maybe I can find it here so you guys can see what I'm trying to say. Let's see if I can find catalytic efficiency.
Wait, back up.
Here we go. Well, yeah, so the other one was turnover number, but yeah, catalytic efficiency. An estimate of how perfect the enzyme is. It measures how the enzyme performs when the substrate concentration is low. And that is the most important property when we talk about enzymes biologically speaking. If you want a list of efficiencies for enzymes, there's a whole list of numbers here. Notice they have wildly different Kcats and Kms, but then when you actually calculate their efficiencies, they're pretty similar in efficiency. There's one property you should know, especially about catalytic efficiency, is that there actually is a maximum limit to it. And let me flip back to the document camera. So there's a maximum limit called the diffusion limit. Which has a value of around 10 to the 8 molar per second. So if you calculate your catalytic efficiency and it's anywhere near 10 to the 8, even if it's higher than 10 to the 8, like if the math comes out that it's higher than 10 to the 8, physically speaking, it will only be as fast as 10 to the 8th molar per second, which is an extremely fast rate. The reason why that is when an enzyme is this efficient, is able to catalyze reactions at this speed, the reaction is no longer limited by the enzyme. It is limited by how quickly molecules spread out in solution. That's what the diffusion limit means, is that, okay, the limiting step is no longer the enzyme. The limiting step is the molecules have to spread out in solution. It's more of a physics reason, but that's basically what diffusion limit means. Yeah.
So on a test, if we're asked to calculate this and we do get higher than 10 to the 8th,
Mm-hmm.
so we have to pick 10 to the 8th, we have to know that we can't.
You will probably get some numbers that are above 10 to the 8th, but only one answer choice will be above 10 to the 8th. So you may get a question that asks which one's the most efficient enzyme or something like that. Or which of the following enzymes is at the diffusion limit. So one of them will probably come out to a number like that.
But like the one you said before, you're like, which one is the most efficient? And you said only one will be higher than 10 to the 8th. Should we pick 10 to the 8th because that's the only one that is the most it could ever be, or no?
No. And what I mean by that is that mathematically you can get numbers higher than 10 to the 8th. So still pick whatever the highest number is.
Okay.
But biologically speaking, you can calculate infinity efficiency. But biologically speaking, you won't go faster than 10 to the 8th because the enzyme is no longer the limiting factor anymore when it's that fast. It's the molecule's fault that it doesn't go faster.
So is that kind of like there's too much product around the enzyme? So
that one, you're thinking of a feedback inhibition or something similar to that. We'll go over that in chapter 15, but that's something later down the line. This is something else. But don't worry too much about it. Honestly, probably the most likely thing is just recognizing this vocabulary term, that something with an efficiency of 10 to the 8th is at the diffusion limit. I just get interested in talking about why that means that, because nobody talks about it. But it basically means it's so fast the enzyme is not the problem anymore, it's the substrate is the problem. All right, so Kcat is calculated this way. Catalytic efficiency is calculated with Kcat over Km. Finally, now we have to actually figure out how to get numbers for Vmax and Km. So that's going to be the next thing that I talk about. 99.9% of the time, the way you get the values for Vmax and Km for a reaction will be from a graph. Just in case, and I don't know yet because he hasn't made the exam yet, there used to be a formula you had to know, and that was the Michaelis-Menten equation. So let's see if I remember this. I never am sure. I believe it is this. You used to have to know this. I haven't seen this in a while, but you used to have to know this equation. It's the Michaelis-Menten equation. And if you plot this equation, this is the equation that makes this shape on the graph. Okay? And there are certain values you recognize. Vmax is here, Km is here, the speed of the reaction is the y-axis value, and the substrate concentration is the x-axis value. Okay, so you used to have to, and again I'm giving this to you just in case it shows up again, you used to have to calculate either Vmax or Km using this formula. He would give you maybe the substrate concentration, the speed of the reaction in Km, and you'd be asked to calculate Vmax. Or he'll give you the Vmax, the substrate concentration, and the speed, and you'll be asked to calculate Km. Basically, it's like an algebra class question. It gives you everything but one thing. You solve for that missing thing. We're not even going to bother doing any practice examples of that because it is just algebra, and all you have to do is memorize the equation, and it isn't very likely to show up on the exam. I'm just giving it to you for context purposes. The most likely way to find Vmax and Km that you'd be asked to do so is by looking at the graph. And so, we already know how to get Vmax. Let's just look at the asymptote here on the graph, and we'll do an example in a little bit. Km, unfortunately, is a little hard when you're looking at this graph. I will give it to you. You'll find that when we have Lineweaver Burke graphs, it's a million times easier. If you want to get Km from this graph, the very first thing you need to do is find where half the maximum velocity is. Okay? So first you find where Vmax is. That's easy. Let's say it's like 10. So in order to get Km, you go to the point that's half of the maximum. So you go to wherever it says 5 on the y-axis. Okay. Next, you draw a line straight to the right from that till you hit your graph. So right here. And Km is whatever the x-coordinate is of this. Whatever number you see right here is your value of Km on this graph. The reason why that is, and I used to teach people this second method, but people would always get confused about it, is that Km is the substrate concentration when the speed is half the maximum. Okay, it does not mean Km is equal to Vmax over 2. That is what a lot of people get confused about. This statement does not mean Km equals Vmax over 2. What this statement means is, find where Vmax over 2 is, which is this dot here, and whatever the substrate concentration here is your value for Km. Okay? That is sometimes you're asked to do this. I believe there is one slide in your notes that illustrates this property as well. I am just stressing to you guys that this is what it actually means, is that the value of Km here is whatever the substrate concentration is when the speed is half the maximum. So you find Km by finding first where half the maximum is. All right. So that's how you find Vmax, and that's how you find Km on this graph. And in the unlikely chance it's an equation question instead, just plug in the numbers you're given into this formula and solve for whatever's missing. Okay. Now, that's this version of the graph. There's another graph that you may be asked about that you'd have to also calculate or determine Vmax and Km from, and that is the Lineweaver Burke graph, which I'll go over right now. Okay. So, this is what's called a Lineweaver Burke graph. All it is that same graph on the other page, but everything is inverted. What I mean is that on the y-axis, instead of speed, you have values of 1 divided by the speed of the reaction. And on the x-axis, instead of substrate concentration, you have the value of 1 divided by whatever the substrate concentration is. The reason why that is that this does a mathematical trick where it turns this curved graph, and mathematically, it turns into a nice linear graph, which is great because linear graphs are so much easier to read, right? Y equals mx plus b. You can find the y-intercept and it probably means something. You can find the x-intercept and it probably means something, and the slope as well. Does anyone know what does the y-intercept represent? What value? Yes.
Vmax?
It is 1 over Vmax. Be very careful with that, but it does help you figure out Vmax. So I'll write that down, and we'll practice doing this. But when you are given a Lineweaver Burke graph, it's describing the same thing as the previous graph. It's just doing so in a linear form. Mathematically, it is my opinion that it is much easier to calculate Vmax and Km if you're given this graph. So you might be given this graph. So if you wanted to calculate Vmax using this graph, look at whatever value the y-intercept is and calculate Vmax from this formula. Process of elimination, the x-intercept is probably going to tell you something about Km, and I'll give you that formula. Okay. The x-intercept, whatever number this is here, is equal to negative 1 over Km. Okay? So, once you have whatever value of x-intercept is, and very clearly it's going to be a negative number, right? Because this is where 0 is. You get weird math situations with the Lineweaver Burke graph, but don't worry, don't overthink it. Whatever the x-intercept is here, you can calculate Km using this formula. Okay? And you might be asked to do that. This is the most common way that it is on the exam, where you're given this graph and asked to calculate Vmax or Km. Okay? And they extend it also, is that once you calculate these values, then part 2 question might ask, what's the catalytic efficiency? Well, you're given Km, you're given Vmax, you might be able to calculate Kcat somehow. We'll practice that in a little bit. But these are the first few things you should be able to do when you're talking about enzyme kinetics, is identify the numbers, conceptualize what a graph is trying to tell you. Okay. Any questions on interpreting graphs of Lineweaver, Burke, or the Michaelis Menten one? Okay. So now we're going to add one more complication, and that is inhibitors. All right, I assume he covered competitive, non-competitive inhibitors already? Okay. So we'll do this. And it is very important that I stress this stuff, because this is probably the most complicated type of stuff you get on exam 2. The rest of material that shows up on exam 2 is memorization stuff. This stuff sometimes isn't as easily studied. So, inhibitors. In this class, there are only 2 types you have to worry about with Michaelis Menten enzymes: competitive and non-competitive. For the MCAT, you have to learn uncompetitive and mixed type inhibition, which we're not going to cover for this class. That is for the MCAT. So, they differ simply on this. Here's an enzyme, here's an active site, and here's a substrate. Did I say active site? This is active site, this is an allosteric site down here. Competitive inhibition, the way it works is that there is an inhibitor that competes with the substrate for the active site. Exactly. Okay, it is competing with the substrate for the same spot on the enzyme. And because of that, the competitive inhibitor will look similar in shape and structure to the substrate, because it has to go to the same spot, so it must look similar, but it's probably not exactly the same. I have this like extra little tail here to illustrate that. But what a competitive inhibitor does, again, is that it competes with the substrate for the same spot on the enzyme, which is the active site. And in order for it to do that, the competitive inhibitor must look very similar to the substrate. What does this end up doing? Well, if the competitive inhibitor binds to the active site, the enzyme is unable to catalyze a reaction with the substrate. So you are inhibiting the reaction. The speed of the reaction is going to go down. Let's contrast that with non-competitive inhibition. So this one is competitive. This one is non-competitive. The way non-competitive inhibition works is the inhibitor does not compete with the substrate for the active site. The only other place for it to go is this adjacent site here, which we had a vocab term for. What do they call this site? Allosteric site, exactly. So, non-competitive inhibitors will go to the allosteric site instead, meaning the enzyme can freely grab the substrate without any problem. Except when the non-competitive inhibitor is there, the enzyme is unable to actually convert the substrate into product. The enzyme can still grab onto the substrate, it just is not able to convert it into product. So that is what non-competitive inhibition does. The end result is going to be similar to competitive inhibition. Well, if the enzyme can't convert the substrate into product, you slow down the reaction. Okay, so both of these inhibit the enzyme, but in different ways. All right. Do you remember this diagram here? Let me draw it out real quick. This is the Michaelis Menten diagram, right? It's a short summary of what the Michaelis Menten theory is that enzyme and substrate come together to form the enzyme-substrate complex, and then when enough energy is acquired, the enzyme-substrate complex, the enzyme is able to convert the substrate into product. Looking at our drawings of this stuff already, the substrate, is it able to bind to free enzyme? The answer is yes. There's no, not substrate, the inhibitor is able to bind to the free enzyme. Why? Well, because there's no substrate there yet. The inhibitor can just fit right in. But is a competitive inhibitor able to bind to the enzyme-substrate complex? The answer is no, and why is that? Well, in the enzyme-substrate complex, the enzyme already has grabbed onto the substrate. The competitive inhibitor is unable to bind to an enzyme-substrate complex. It's a subtle little difference here, but that also affects how these two classes of inhibitors affect enzymatic reactions. So let me write that down. Competitive inhibitors only bind a free enzyme, which I'm only going to denote as the capital letter E. Can anyone tell me then, what is a non-competitive inhibitor allowed to bind to? Allosteric site, yes. I should have been more specific. Let me ask one at a time. Is a non-competitive inhibitor able to bind to a free enzyme?
Yes.
The answer is yes, okay. What about the enzyme substrate complex?
Yes.
The answer is yes also. Why? Well, the non-competitive inhibitor does not care about the active site. It doesn't care that the enzyme is already grabbed onto its substrate in this part of the diagram. Therefore, a non-competitive inhibitor can bind to the enzyme or the enzyme substrate complex. That, again, affects, it gives it a little bit more flexibility. Non-competitive inhibitor, in fact, is probably going to inhibit enzymes more often than a competitive inhibitor because a non-competitive inhibitor has more options. Okay? When you learn about uncompetitive inhibitors, if you're studying for the MCAT, it is simply this. I will not write it on here so I don't confuse anyone watching the video. But uncompetitive inhibitors only bind to the enzyme substrate complex. Uncompetitive, that's for the MCAT. Okay? That's the subtle difference between these types of inhibitors. Alright, so inhibitors. Last thing with inhibitors, and then we're going to practice some graph stuff, is what happens to Vmax and Km when dealing with competitive inhibitors and non-competitive inhibitors. So. Okay. And I'm going to create a table here, and we're going to look at what it looks like on a graph in a little bit. What does a competitive inhibitor do to Vmax? I'm going to give you these values, and yes, you can choose to memorize them, but we'll explain it when we see the graphs. A competitive inhibitor will not alter Vmax, so I'm going to put constant. Vmax is going to stay the same. It will not be affected. For a competitive inhibitor, it will actually cause Km to increase. Okay. For a non-competitive inhibitor, it'll cause Vmax to decrease, but Km will be constant. Okay? There are two ways to do this. One is just straight up memorizing this table. It'll help you tremendously when you start analyzing the graphs in a second. The other thing is to kind of understand conceptually why this stuff happens. So let me do so by illustrating it on a graph. Okay, so has everyone got this written down? Okay, so we're going to practice it. All right. So, actually, there might be a better looking graph in the notes. Let's see. I won't do the Lineweaver Burke one yet. Let me go to this one, yeah. Okay. So, this is the same hyperbolic shaped graph that we were talking about with the enzymes. This pink line here represents the regular enzyme. There's no inhibitor or anything, and we notice the same properties, right? There's substrate concentration here, velocity there. As you increase substrate concentration, you increase the rate of the reaction until it reaches a saturation point. This graph also includes what the shapes would look like, how they would change, how the graph would change shape if a competitive inhibitor was added to this enzyme, or if a non-competitive inhibitor was added to this enzyme. And it changes the shapes quite differently. Despite the fact that both inhibit the enzyme, they do so differently. Let's explain why. For a competitive inhibitor, the inhibitor is competing with the active, so competing with the substrate for the same active site. So how do you beat that? If you wanted to counteract competitive inhibition, how do you beat that? The answer is you add more substrate. Why is that? Well, if you have, let's say, 5 competitive inhibitor molecules and 5 substrate molecules, the enzyme is only going to pick correctly 50% of the time, right? Because there's 5 inhibitors to choose from and 5 substrate to choose from. What happens if you increase the substrate concentration to the point there's like 10,000 substrate molecules, but still only 5 competitive inhibitor molecules? The enzyme is going to pick correctly more often. So a feature of competitive inhibition, therefore, is that at high substrate concentration, it's like nothing happened. And why that? Well, the reason why that is because if you have plenty of substrate available, it doesn't matter that there's competitive inhibitors. The enzyme is going to pick the substrate more often. Okay, so I'll stress that again. A feature of competitive inhibition is that Vmax is the same. It will be constant. That's what you wrote down on the other on the page over there. And again, that is because if you just flood your enzymes with substrate, the competitive inhibitor can't win for the active site. Yes?
So it's only at high concentrations of substrate?
Yep, and you can see that here is that at low and kind of medium substrate concentrations, look at the rate of the reaction, and it is less than the pink line here. It is slower at literally every other point in this graph. And the only time it catches up is at high substrate concentration. Okay. Well, what happens to Vmax for non-competitive inhibition? So, one thing with non-competitive inhibition is that because it doesn't interfere with the active site, it doesn't bind to the active site, it inhibits the enzyme by kind of like shutting it down. That is what a non-competitive inhibitor does. It kind of shuts down the enzyme. Because of that, it doesn't matter how much substrate you add, there is the limit, the maximum speed of it is going to be a lot slower than without the inhibitor. So think of it like this, is that a non-competitive inhibitor basically shuts off enzymes. That is why Vmax is so much smaller here. Competitive inhibitors don't do that. Competitive inhibitors, all you have to do is add more substrate and it's like nothing happened. For non-competitive inhibitors, you add more substrate, you're still in trouble. Vmax is still less here. Okay, so that explains why we wrote those values for Vmax on the other side of on the page a second ago. So what about Km then? Okay, we said that what competitive inhibition does to Km is that it increases the value of Km. We said earlier that Km tells you something about the enzyme's ability to grab onto substrate. The competitive inhibitor goes to the active site, right? That's directly interfering with the enzyme's ability to grab onto substrate. So that means the enzyme is having a tougher time of grabbing onto the substrate when a competitive inhibitor binds to it. So that explains why Km goes up, right? Remember, a high Km is bad. A high Km means the enzyme is terrible at grabbing onto substrate. So when you have a competitive inhibitor, Km will go up. The enzyme is not doing a good job of grabbing onto its substrate. Non-competitive inhibitor, though, doesn't touch the active site. Non-competitive inhibitor doesn't do anything to the active site. The enzyme can still grab onto its substrate without any issues. So that's why non-competitive inhibitor does not change the value of Km. It does not change the enzyme's ability to grab onto substrate. So that's the kind of explanation on all that. Let's see, anything else I wanted to mention with this? Anyone have any questions on the conceptual stuff? We're going to do some practice right now. Okay. So, where did I put the worksheet here? Here we go. Okay. Let me put it all on one page real quick.
So for
Yes.
competitive inhibitors,
Yes.
whenever it gets inhibited, it just spits out the inhibitor, and then it can be used again.
Yes. We talk about competitive inhibitors and how they interact with enzymes, right? Yeah. Competitive inhibitors only bind to their enzyme temporarily. They can bind and then fall off, and a substrate can come in. It's kind of like a very transient thing. Non-competitive inhibitors, most of the time when they bind to their enzyme, they're shutting it off. But I don't know of every example, so I can't say one way or the other there. But the general concepts you guys have now. All right. So I tried to kind of use the same analogy that Dr. Hasey's did, so let's see if we can break this down. This should be actually quite easy now that you guys have the introduction here. There's an enzyme called apelase, I guess it's his brother, and it catalyzes the following reaction. Here's a substrate, the apple, and his brother converts it into an apple core and apple slices. That is all the reaction is, that there's a reactant and there's products and there's an enzyme that does the reaction, okay? And all the enzyme does, I should say, and I should emphasize, all the enzyme does is it speeds up the reaction, okay? So maybe that analogy doesn't work exactly here. All an enzyme does is it speeds up a reaction. Without the enzyme, this reaction does technically happen, it's just a lot slower. All right, several experiments are done to determine the properties of this new enzyme. First, scientists wanted to measure how much faster the reaction occurs when it is catalyzed versus when it is uncatalyzed. The term used to describe this property is called catalytic power. It's earlier in your notes. They determined that without this enzyme, the rate of consumption of this reactant here was a value of 0.01 molar per second. But when the enzyme was included, the rate of consumption increased up to the point of 1 molar per second. What is the catalytic power of apelase? Anyone know?
100.
The answer is 100. How do you know that? What's the formula for catalytic power?
I mean, catalyzed over uncatalyzed.
That's efficiency. Sorry, I probably should have stressed. And what is that?
Catalyzed over uncatalyzed.
All right, so yep, that's right. I'll write it down here. So catalytic power, sorry, I probably forgot to talk about catalytic power last SI session. Catalytic power is the rate of catalyzed reaction divided by rate of uncatalyzed reaction. Okay, let me bold this. So this is actually a lot easier to calculate than a lot of the other numbers where we have to read graphs and do some other previous calculations. All catalytic power is, and you will be given these two pieces of information here, all it is the rate of the catalyzed reaction divided by the rate of the uncatalyzed reaction. So in other words, the rate of the fast one divided by the rate of the slow one. And what we do here then is we plug in 1, and then we divide it by 0.01 for our example here. If you plug that into a calculator, you will find that comes out to 100. So this enzyme has a catalytic power of 100. All right. And there are no units for catalytic power, so the numerical answer is the only thing you have to worry about. Okay. Any questions on catalytic power? I admit I forgot to talk about that, but that's because it's, as you can see, a pretty easy thing to calculate. All right. Next, the scientists varied the concentration of the reactant, meaning they either had a lot of apples or very few apples, and they measured the resulting rate of the reaction. The reaction rate changed depending on how many apples there were. The following are two plots of their results. Use either of these graphs to determine the Vmax and the Km of the catalyzed reaction, the Vmax and the Km of this enzymatic reaction. And I'll scroll down to one of the graphs here. The black line is the mathematical asymptote the computer calculated for the data. And the units for reaction rate are molar per second. That's because I forgot to include it here. And the units for substrate concentration are molarity for this problem. All right, using what you know, using this graph, we'll do both graphs. We'll use this one first. What is the Vmax of this reaction? It is 100. It is very simply, you look at whatever the asymptote is, where the reaction starts flattening out. Let me zoom in a bit more.
Are we going to be given the line for the asymptote?
It'll be, the reason why I drew the line here is that Excel didn't show it very well. On the exam, the asymptote will be very obvious.
Okay.
And in fact, you might even see it on the practice exam, I can't recall, but it'll be very obvious what the asymptote is on the exam. Okay, now for the slightly harder thing to do. What is Km for this reaction using this graph?
10.
It is 10, exactly right. Well, let's break it down here. You remember that shortcut to find out Km is that first you need to find what? Vmax over 2, right? You have to find the Vmax over 2 spot. Well, in the previous answer here, we said that Vmax was 100. Therefore, Vmax over 2 must be 50. But is 50 the answer? No. Remember that Km is whatever the x coordinate is, whatever the number is down here, at a speed of Vmax over 2. So, Km is equal to 10, in this case. 10 molar would be the units for Km. All right, again, I'll reiterate, Km is, all you have to do is find where Vmax over 2 is. Well, Vmax is 100, so Vmax over 2 must be 50. You go to that spot there, and you go straight down. Whatever number that is your value of Km for this graph. Okay, any questions on this graph?
Is there a unit for Vmax?
Vmax would be molar per second. Yeah, it'd be the same unit as the y-axis, which is molar per second. Oh, sorry about that. Yep. All right, well, we'll have to end right now. And the unit for Km is just molar. It's the unit of the x-axis. All right. Well, we'll do Lineweaver, Burke, and inhibitors next time. And we'll definitely start on chapter 15 as well. If anyone has a sign-in sheet, please bring that up here.